Hello and welcome again to my physics video lecture supplements series. Today I wanted to do a brief example involving a weighted arm. Basically, how much force do your muscles have to put on the elbow joint in order to hold up some weight? So there's actually two sets of muscles that are working on your elbow. I'll turn to the side. There's two sets. One set is, of course, your bicep muscles are the main muscles that are holding your arm up. There's actually a second set, your stabilizers, your tricep muscles in the back of your arm, that you also need to have exert some force in order to actually make both the total force on your arm and the total torque on your arm both balance out to zero. So if you're holding some object at arm's length, if you will, then that basically means that you have a system in equilibrium, and that system consists of the weight of your arm and the weight of the object that you're trying to hold in your arm, both pulling downward and both trying to torque your arm downward. And then the muscles within your bicep trying to torque your arm upward. And then your stabilizer muscles in the back essentially not applying any torque depending upon where you want to pick your axis of rotation. Usually you pick your axis of rotation to be the elbow or the very end of the arm. So I've gone ahead and drawn on the board a little mock model of what a weighted arm may look like. I've decided to pick this arm to be holding a book or some other object such that this other object has a mass of 4 kilograms or a weight of 39.2 newtons. And then the arm itself also has some weight which acts at the center of gravity for the arm. And maybe your arm is 2.5 kilograms. I guess that's kind of give or take depending upon how large your arm is. In other words, how long is it? How muscular are you? How dense are your bones? But this seems like a reasonable estimate. And I should probably, give credit where credit's due here, I borrowed an example from the OpenStax college physics textbook. So these numbers come straight from that example, but I'd like at the end to maybe also look at what happens if you lengthen the arm. So basically what we have is a pivot point that's chosen to be the elbow itself. And we take the triceps muscles, or the muscles that are pulling such that it's like an effective push down on the elbow, to be working right at the axis of rotation. I take the biceps muscles, therefore, to be working not on axis of rotation, but some distance away. Call it 4 centimeters. OpenStax certainly does. And then you have the weight of your arm itself acting at the center of gravity for the arm, which is maybe 16 centimeters from that axis of rotation. And then the book acting clear out towards where your hand is, maybe a full 38 centimeters away from your axis of rotation. So to solve for the amount of force that's being supplied by both the triceps muscles and the biceps muscles, we basically need to set up an equilibrium condition. And so what that looks like is that the sum of forces and the sum of torques are both going to be 0 for this system. So we have this right here is going to be 0, and we have this as 0. So forces, torques. And now that we have an axis of rotation picked, we can write out what the torques look like, and we can write out what the forces look like. So the forces are basically going to be this weight and the stabilizing force all acting down, and the biceps acting upward. So basically force from biceps minus force from triceps or from elbow minus the weight of the arm and minus the weight of the book all have to equal 0. And then secondly, the torques add to 0. So the torques are this one, since it's acting at the axis of rotation, is providing 0 torque. And so what we're left with is the biceps times the distance that the biceps are working minus the weight of the arm times the distance that the arm is going to work at minus the weight of the book times the distance that the book is going to work at. All these things add to 0. So we might as well solve this equation first, because at this point it has one unknown in it. That's why we choose the axis of rotation to be here where the triceps muscles are working. And so this one right here basically tells us that force from the biceps is going to be equal to the sum of these other two torques divided by the radius at which the biceps themselves are working. So we can plug numbers in: 4 centimeters, 16 centimeters, 38 centimeters for these distances. And since they're all centimeters, we can actually leave them in centimeters. We don't have to convert to meters if everything's in centimeters. So force from the bicep is going to be, we've already done the math to get the weights here, so 39.2 newtons. Excuse me, for the arm it's actually 24.5 newtons times 16 centimeters plus 39.2 newtons multiplied by 38 centimeters. And all of that gets divided by 4 centimeters. So what we're going to end up getting is, when you plug all those numbers in, you get 470.4 newtons. And I notice that of these things, sorry, this should be 4.0 centimeters. Of these things, we have 2 significant figures to work with, and so the answer needs to be in 2 sig figs. So this right here becomes just 470 newtons. So I'm going to go ahead and write that over here. So force from the biceps, 470 newtons. Okay, what about the triceps? how much do we get from the triceps? Well, okay. That just involves solving this equation for the triceps muscles and plugging numbers in. So this guy right here yields force from the triceps is force from the biceps minus the weight of the arm minus the weight of the foot. So 470 newtons minus the 24.5 newtons minus 39.2 newtons. And so what that ends up giving us is a total force of 406.7 newtons. But again, we should round to two significant figures. So we end up getting that the force supplied by the elbow is approximately 410 newtons. Okay, so that's how much total force is being supplied by both the biceps and the triceps. A second question is, well, what if you have a longer arm than that? And the answer is, well, it depends upon whether we're going to lengthen the arm and try to keep everything the same weight or what. Usually a longer arm also means a heavier arm, but for the sake of argument, if we just lengthen all these lengths proportionate to each other, so maybe we go from 4 centimeters to 5 centimeters. We go from 16 to 20 centimeters. We go from 38 to 47.5 centimeters. If we do that, and if we don't actually change any of these weights, which I guess includes changing the weight of the arm, what we find is that when we plug the numbers in over here, so this becomes a 20, this one becomes a 47.5, and this one becomes a 5. And it turns out that we basically just multiplied every number in this equation by the same factor, and so we end up getting the same numbers at the end. So the length of the arm doesn't matter as long as everything's proportionate, other than that the arm probably gets a little bit heavier as it gets longer. And so that ends up having some effect right here. This number maybe changes by a factor of, I don't know, maybe that length cubed, for example, if you treat it as a solid object. Everything's getting proportionately bigger, in other words, so it gets longer, and the radius also gets larger by a proportionate factor. So you have a length cubed effect on the total mass. So that would be the only reason why anything would change. Or if, for example, the arm is longer, but the bicep, for example, works in the same place, that might have an effect because now you're not multiplying every single number in this equation by the same factor. But so long as you keep everything proportionate, except for the mass of the arm, length ends up not mattering a whole lot. So that's it for now. Hope that you've enjoyed this video.